In this video, we'll look into the design of reinforced concrete columns. Columns are basically vertical elements that carry the loads from slabs or beams and then ultimately transfer it to the foundation of the structure. Columns essentially carry the vertical loads, but sometimes it can carry the horizontal loads or the bending moments as well. The bending moments in columns mostly come from the loading from earthquakes or wind, or even from the eccentricity of the columns. It can cause the bending moments in column as well. So apart from the vertical loads, we have to design the columns for the horizontal loads or the bending moments as well. So these are some examples of columns, as you can see in buildings or in the bridge piers. You can see the columns in different shapes. They can be square or rectangular or circular columns, or they can come in other shapes like irregular columns or blade columns. Blade columns are usually used so that the column flush with the thickness of the wall, so it doesn't protrude out of the walls. Or they can be encased column, as you can see here. So encased columns uses the steel members like I-section as a reinforcement within the concrete column. So instead of using a reinforcing bars, it uses the steel I-section as a reinforcement itself. And there can be other columns like steel tubes filled with concrete as well. So in this kind of column, steel hollow tubes are used as the permanent formwork, and the concrete is poured inside it. And the steel also acts as the reinforcement for the column, and it acts as permanent formwork as well. So these are the different types of columns, concrete columns, that you can see. Here are some pictures of concrete columns. So it is a circular concrete column. The picture is from the Science Place building just below the big lecture theatre. And the second example is the blade column. As you can see, the blade columns has a very thin width and are very long, so that the width flushes with the width of the wall itself, so it doesn't protrude out of the wall. These columns in here, they are hollow steel tubes filled with concrete. This is from Southern Cross Station in Melbourne. And up close, these are concrete filled steel columns. They are around 40 meters apart, supporting the steel roof of the Southern Cross Station in Melbourne. Now, when we consider the failure mode of reinforced concrete columns, we can divide it into two failure modes. The first one is called as the crushing of the concrete columns. When the vertical load acting on the column exceeds its load carrying capacity, the concrete will finally crush or yield, as shown in the picture here. This kind of crushing failure occurs typically for a stocky column, like most of the reinforced concrete columns are stocky. That means it has relatively large cross-section area. Then the column is more likely to fail in crushing. Another type of failure mechanism of columns is called as the buckling failure. This kind of failure mode is more critical for slender columns, like for steel columns or for timber columns, where the cross-sectional area of the member or the column is relatively small, and it is very slender and it is very long. In the buckling mode of failure, when the vertical load reaches the critical buckling load, the column will become unstable and it will start to buckle before it reaches its crushing or yielding load capacity. But for reinforced concrete columns, usually the failure mode is the crushing failure, as the reinforced concrete columns are usually stocky or have large cross-section area. This kind of column is called as the short column. So for this lecture, we'll mostly be focusing on short reinforced concrete columns. Now, for the short reinforced concrete column subjected to axial load, if the column is subjected to pure axial load, that means the load is acting centrically, then the column is subjected to pure axial stress, as shown here. This is a square column with 4 longitudinal reinforcement, and it is subjected to centric loading. And you can see that the stress will be uniform across the cross section. It will be pure axial stress. the compressive stress is taken by the concrete as well as by the steel, and in this case the steel is yielding, so it is denoted as FSY as the steel stress, and the concrete stress is denoted as alpha 1 FC dash. We'll talk about the alpha 1 in a second. And the strain diagram is shown here, and it is also uniform across the cross section of the column, and the strain in the concrete corresponding to alpha 1 FC dash stress is taken as 0.0025. We'll talk about this one in a second. Now for this column, the ultimate strain capacity of this column is given by the combination of the load taken by the concrete plus the load taken by the steel in the column. Now if we denote the ultimate load capacity as Nu naught here, the load taken by this concrete is in this equation. The area of concrete is the gross area of the column, that means all of this, minus the area of the steel, AST, that will give you the area of the concrete alone. So that is the area of concrete cross section without the steel, and multiplied by FC dash, that is the characteristic compressive strength of the concrete, multiplied by the factor alpha 1, which is given by this equation in clause 10.6.2.2. Now alpha 1 takes into account the size effect that has to be taken into account, because FC dash, the characteristic compressive strength of the concrete we obtain from the cylinder test of a cylinder of 100 millimeter diameter by 200 millimeter length, but the concrete column is much bigger than that, so there can be some size effect. So instead of using FC dash directly, we are considering that for the large column there is a possibility that there can be a segregation causing the degradation in the strength of the column compared to the strength of the cylinder. So to take that into account, take that size effect into account, we use alpha 1 FC dash instead of using FC dash directly. So this is the strain taken, the compressive strain taken by the concrete, and this is the compressive force taken by the steel. That means area of steel, AST. So the area of steel includes all of these 4 reinforcement, that is AST, multiplied by the yield strength of the steel, FSY. So if your column is subjected to pure axial force, then the total failure capacity of the column is the combination of the compressive strength of the concrete, which is given by the first part of this equation, plus the compressive force taken by the steel, which is given by the second part of this equation. So that will give us the maximum compressive force that the column can take. Now again, the compressive strain in the concrete is 0.0025, corresponding to the alpha 1 FC dash of the concrete stress. Now in the columns, apart from the longitudinal reinforcements, we also have the lateral ties as well. Now these lateral ties are there to improve the shear strength of the columns, but these lateral ties also help to confine the concrete core as well. As you can see in this figure, this column has been damaged and the concrete has pulled out from the cover, but you can see that the core concrete is still intact. The stirrups, as you can see here, these lateral ties, the square lateral ties are holding the concrete core together, and this confining of the concrete core by the lateral ties helps to improve the strength of the concrete and the ductility of the concrete as well. This is the load displacement curve of concrete columns for different scenarios. So the first one, and the first curve, this one, is for the columns with no lateral reinforcements. So if the column doesn't have lateral reinforcement and it is loaded vertically, as you can see, it reaches its maximum compressive strain capacity, Nu naught, and then it will fail. Second case uses the rectangular lateral reinforcement as seen here. So in that case, with the lateral reinforcement, it helps to confine the concrete and it helps to improve its performance. So that means it becomes more ductile. As you can see, there is a yield plateau of the column, and it can deform, and it helps to improve the compressive strength of the concrete column. Now the third one, the spiral reinforcement, as you can see, if we are using a circular spiral reinforcement for the column, then it further improves the ductility of the concrete column. It further improves the performance of the concrete column, because what happens is that if you are using a square lateral ties, these straight members of the square hoops can actually buckle out. When there is enough compressive force, it can buckle out. So that means only this non-shaded portion of the square hoops concrete are being confined using the square hoops. So only this non-shaded portion of the concrete is being confined when we are using the square hoop. But these shaded portions are not confined because the straight portion of the square hoop can buckle outwards, so it may not be confined fully. Whereas for the circular spiral, because of its shape, there develops axial hoop tension in the circular spiral, which helps to confine the concrete core much better than the square hoops. So you can see that the performance of the circular hoops are better than the square lateral ties, but again, having the lateral ties improves the compressive strain much better than the ones that without the lateral ties. These are the examples of rectangular ties and the circular ties here. And this figure shows the importance of the lateral confinement of concrete core. This figure is from 2015 Nepal earthquake, and this is a building damage in Kathmandu, and you can see that the reinforced concrete column has very severely been damaged, and the lateral ties, the square lateral ties in this case, are not adequate. That means it cannot confine the concrete core adequately, hence the concrete core has been damaged, and also the longitudinal reinforcement you can see has buckled out as well. So as soon as the concrete core is not confined properly and the concrete core is damaged, the concrete column cannot take any further load as well. And these are some other examples of column damage. And the first one you can see is from 1971 San Fernando earthquake, and this again doesn't have adequate lateral ties, and you can see the damage in the concrete core, and this column can no longer take any further load, and it compromised the integrity of the whole building as well. Whereas on the other side, this column, even though it is quite severely damaged, it has the circular ties in it, and it is still confining the concrete column quite adequately. So as you can see, the concrete column is still intact. Even though the cover concrete has spoiled, the concrete core is still intact and it's still carrying the load, even though there has been a quite substantial deflection in this column. So this shows the importance of the lateral ties in columns. So when we are discussing about the earthquake loading in columns, it is very important to understand the capacity design concept. Capacity design concept can be easily explained using the chain analogy as shown in the two figures here. The first figure is a steel chain made of high strength steel and subjected to tensile force. So all of the links in this chain is made of the same material, same high strength steel. So when it's subjected to tensile force, as soon as it reaches its tensile strength capacity, the steel chain will fail. But we can't exactly tell where the steel will fail because all of the materials is the same, and one of the links will fail, and it can be brittle failure because the steel itself is very high strength. We don't want this kind of failure when designing the buildings because the failure mechanism is out of our control. We don't know exactly where the failure will occur. and the failure can be brittle as well. However, in the second chain here, the rest of the link is still made of that high strength steel, but one of the link we make it weaker. That means when we subject this chain to a tensile force, it will tend to fail at the weaker link. The weaker link will first tend to fail. However, the trick is that we make that link, the weak link, ductile. That means before it fails, it will go through a large deformation, and it will give us enough warning before the chain will fail. So what we are doing is that we are making one of the links weak and ductile. That means the weaker link will tend to break first, but as it is ductile, it will go through a large deformation before it will fail. So this is the kind of failure that we want in earthquake design, because we know where exactly the failure will occur, and that element will go through a large deformation before it will actually fail. Now, from the building perspective, what we do is that we make the column strong, like these chains. We make them very strong that it can carry the vertical loads, but we make the beams in the building weaker and ductile, as you can see here. So the weaker and the ductile links in the building structure is the beams. That means we want the beam to go through a large deformation before the failure of the structure. And as we discuss in the beam design, we want the beam to be failing in a tension failure mode. That means it will be very ductile, so it can take a large deformation before it will fail. So the capacity design concept is that we want the columns to be stronger, and we want the beams to be weaker than the columns, but we want them to be very ductile. So that means the column flexure strength must be greater than the flexure strength of the beam, so that the plastic hinges are formed in the beams instead of the columns. So as you can see in the left side picture, if the beam sway mechanism where the plastic hinges are formed in the beams is the preferred damage mode, whereas in the right hand side picture, if the plastic hinges are formed at the columns, it can lead to what we call as a catastrophic failure, or the soft-storey failure of the structure. So it can compromise the integrity of the structure. So we don't want this kind of failure, but we would prefer this kind of failure mode in a large seismic loading conditions. Now, if the columns are weaker than the beams, these kind of failures will occur, and we want to avoid this kind of failures. First picture is from Bhuj earthquake in India, which occurred in 2001. As you can see, the building looks fine, but if you look closer, the ground floor of the building has completely disappeared. Usually in residential area in this part of the world, for the ground floor, they tend to remove the walls or even columns to open for garage or even for the retail shop. So the ground floor is relatively weaker and less stiffer than the other floors. So when the earthquake happened, the ground floor is much weaker compared to the other floors, so the failure concentrated in the ground floor, and this is called as the soft-storey failure. And this one is from the right hand side picture is from the Kobe earthquake in 1995 in Japan. And this building again looks perfectly fine, only except that one of the floor has disappeared here. So again, this floor might have been weaker compared to the other floors, and the failure were concentrated on that floor, and the failure of the column lead to the failure of the one whole floor. And some more examples from 2015 Nepal earthquake. So there was a massive earthquake in Nepal in 2015, which was around 7.8 magnitude, and it was only 80 kilometers from Kathmandu, the capital city of Nepal. And you can see some damaged pictures from this 2015 Nepal earthquake. Again, this building looks fine, but if we look closer, the ground floor of this building again has disappeared. Again, this is a very good example of soft-storey failure. Again, because of the opening for the retail shops, the walls might have been removed, the columns might have been removed as well. So the ground floor was weaker, the columns in the ground floor was less stiffer and weaker. So when the earthquake happened, the columns in the ground floor fell, and it resulted in the soft-storey failure like this one. This is another photo from the damage of a building in 2015 Nepal earthquake. This kind of failure is called as a pancake failure. The top story of the building might have collapsed due to different reasons, and once the top story collapses, the load is transferred to the floor below it. The columns cannot take that load, and the failure occurs in that floor. Again, all of the load is transferred to the floor below it. Again, the columns collapse in that building, and that lead to the pancake collapse of this building. Again, this shows the importance of the design of the reinforced concrete column. The failure of the columns can lead to this kind of failures. Again, another failure from Nepal earthquake. There is a large shear failure in this column. So these earthquake damage pictures of reinforced concrete columns and structures underscores the importance of the proper design of reinforced concrete columns. The damage in the reinforced concrete columns can lead to the catastrophic failure of the whole structure. So we have to make sure that the columns are designed properly. Now, even if we don't have to design the building for earthquakes or wind loading, we still have to consider minimum eccentricity that comes due to the construction imperfection in the buildings. For example, when we are building one story and then we are building another story on top of it, the columns may not be perfectly aligned, and that small eccentricity in the columns between the stories can cause the eccentricity in the columns, and that can lead to the bending moment in the columns. For example, in this case, the top column on top of this one is not perfectly aligned. That means it is slightly eccentric, and that causes the bending moment in the column. So what it means is that if we look into this column, so if we transfer this the axial force to the center, apart from that axial force, this column is subjected to bending moment as well, mu, which is given by the axial force multiplied by the eccentricity. So that means this column is subjected not only to the axial force but also to the bending moment as well. So we have to design for this bending moment. Now, for every column, we have to consider this minimum eccentricity when we are designing the column. So the code gives this minimum eccentricity that we need to consider for every column, even though we don't have to consider the lateral loading in the columns. So according to AS3600 clause 10.1.2, the minimum eccentricity we have to consider for every column is 0.05 d, where d is the dimension of the column itself. So the E minimum is 0.05 d. So the minimum eccentricity we have to consider is 0.05 d. That means the minimum moment that we have to consider is the axial force multiplied by this minimum eccentricity. That means Nu multiplied by 0.05 d. So even though we do not have any horizontal load, we need to consider the bending moment, minimum bending moment caused by this minimum eccentricity in the columns.